So now we have a practical issue to deal with, and that practical issue in acid-base reactions comes from the very large dynamic range in the concentrations of H3o plus and the concentration of the hydroxide anion. And we have to find a way of writing this such that we don't have to write out the full expression, but we have to find a shortcut for doing that. And we do that by creating the representation of those concentrations in terms of an operator. And this operator P means that anytime we have a quantity of anything, when we operate on that number with P, it means we're going to take the negative log to the base 10 of that number. So we're going to apply this to virtually every quantity in acid-base reactions. For example, if I take P of the H3o plus concentration, I write that as pH because H is a shorthand term for H plus, which represents the H3o concentration in the solution. And that means that I take minus log to the base 10 of the concentration of H3o plus in solution. Well, I can do exactly the same thing with my OH minus concentration, hydroxide anion. But in this case, I call this POH, which is a shorthand form of OH minus, and that means that's equal to minus log to the base 10 of the hydroxide anion in solution. So pH is therefore a measure of relative acidity or basicity of a solution. And we can write this for a condition of pure water immediately, because we can write that pH is equal to minus log to the base 10 of the H3o plus concentration, and that's equal to minus log of nothing other than 10 to the 7, which is the concentration of H3o plus in pure water, and that gives me a minus of a minus 7, which gives me plus 7 for the pH of pure water. And so we can see how easy it is then when we contract this down by using this P operator to write the concentrations of any species in an acid-base mixture. Now let's take a look at another extremely important aspect of this. Let's suppose the concentration of H3o plus increases, and we're going to see how we do that in just a moment by putting an acid into water. But the crucial point is that because we write this equilibrium constant for water reacting to form H3o plus and OH minus, we call this the equilibrium constant for water, and we know that that's equal to the concentration of H3o plus times the concentration of OH minus, but we also know that this is equal to 1 times 10 to the minus 14. So if we have 10 to the minus 7 for the concentration of the hydronium cation, we can calculate the concentration of the hydroxide anion, and we know it must be 10 to the minus 7 in order to get the product equal to 1 times 10 to the minus 14. So this is interesting. This says that this increase in H3o plus means that OH minus must decrease, because the overwhelming reaction in an acid-base reaction is driven by that release in Gibbs free energy that profoundly favors H2O liquid over H3O plus and OH minus. And so this equilibrium constant means that anytime I increase H3O plus, OH minus has to drop such that the product is always equal to 1 times 10 to the minus 14 at 298 Kelvin. So we're moving in on some extremely important conclusions, because if we write the equilibrium of water resulting from autoionization, and we've now done that a number of times, but this autoionization means that this profoundly important characteristic of water, created by its polarity between the oxygen and the hydrogen, generates the production of H3O plus, and the aqueous phase, and the hydroxide anion also in the aqueous phase. But we now know a great deal because we can write pH of this reaction and add that to pOH, and we can write that out immediately. That's minus log to the base 10 of the H3o plus concentration, and then we add to that plus a minus log to the base 10 of the hydroxide anion concentration. So let's put brackets around this just to remember the negative sign that's there. And we can write that by gathering together the logarithms, and that gives us minus log to the base 10 of the product of H3o plus times the OH minus anion. But we also know that this is equal to pK water, and we know that pK water is equal to minus log to the base 10 of 1 times 10 to the minus 14, which is equal identically to 14. That's quite remarkable. That means that I can write P of K water equal to 14. And so now we have a relationship between pH, pOH, and pKw. It turns out that that's going to be a very, very valuable expression. So from this point on, we can write the equilibrium constant for H2O liquid reacting with itself to form the H3O plus hydronium cation in aqueous solution plus the OH minus aqueous anion, and we can designate this henceforth as an equilibrium constant that is specific just to this reaction, and that Kw is equal to the product of H3O plus and hydroxide minus, and that's equal to 1 times 10 to the minus 14 at 25 degrees C, or 298 Kelvin.